Ideal op-amp characteristics are open loop gain is infinity. That is, you have already seen this open loop gain. Where it is? Somewhere this one. Okay. So this is open loop gain. AOL. This open loop gain should be infinity. What is this one? This is a voltage dependent voltage source. So this is a dependent voltage source. Its voltage is dependent on this value. Okay. So this is AOL open loop gain. Its value should be infinity ideally. Okay. And the voltage difference of the two inputs is magnified infinitely. It's true something like 2 lakhs, means the difference between plus and minus terminals can be amplified to 2 lakhs times. Let us suppose the difference between the two input signals is 1 volt, sorry, 0.0001 volt. It is amplified by 2 lakh times, means 2 lakhs into 0.0001, means we will get 200 at the output, something like that. Infinite input impedance, no current allows into the input terminals. It is true that its value is 10 power 12 for FET op-amps, FET based op-amps. Earlier we have seen transistor based op-amps. If the same op-amp is designed with FET, field effect transistors, its input impedance is 10 power 12. Zero output impedance R naught. Rock solid is independent of load. Rock solid independent of load means whatever the load we are connecting, its output impedance is very low. This is a very important property. We will see what is the purpose of this in some other with a proper example. I mean application of op-amp. Roughly true to current maximum 5 to 25 milliamps. Will allow the current from 5 to 25 milliamps at the output side. Infinitely fast means its bandwidth ideally should be infinite. In this case, what is the bandwidth? 14 kilohertz. Practical op-amp, it will fall at certain frequency. The gain will not maintain constant throughout all the frequencies like this. This is ideal case, means not practical, not available practically. Ideally speaking, it should be like this, but practically it will be like this only. Means ideal op-amp will allow all the frequencies, means the bandwidth should be infinite. Slew rate is 0.5 to 20 microvolt per second. I will tell you what is slew rate in the next slides. It is limited to a few megahertz. Okay. Zero offset voltage, that is V naught equal to 0 when V1 and V2 are zeros. I already told you when V1 and V2 are 0, if we have some voltage at the output, that output is known as offset voltage. If it is 0, that is okay. If it is not 0, we have to apply some extra voltage at the offset voltage pins, what we have shown in the first slides, so that we can make V naught as 0. It can be seen that an ideal op-amp draws no current at both the input terminals because of the infinite input impedance. Any signal source can drive it, and there is no loading on the preceding driver stage. Driver stage means what is the loading? If it is drawing some current into it, then it acts as a load for the source what it is feeding to it. We will discuss this thing also in the next slides. What is this loading effect in detail? Since gain is infinity, voltage between the inverting and non-inverting terminals, that is a differential input Vd equal to V1 minus V2, essentially 0, or V out output voltage is V0. Output voltage V0 is independent of the current drawn by the output as R0 equal to 0. Okay, the output can drive an infinite number of devices. Means you can connect ideally many devices, infinite number of devices at the output of the op amp, but practically it is limited to certain number of devices only. Okay, we cannot we cannot connect infinite number of devices outputs, infinite number of devices at the output of the op amp. Okay, that's not possible. Concept of virtual grounding. Virtual grounding means, actually if you see, this is negative and this is positive inputs of the op amp. If this is grounded, this is also grounded. Okay, this is physical grounded. Physically we are wantedly connecting it to ground, but if you measure the voltage at this point, this is 0. If you measure the voltage at this point, this also be same as this one. Okay, that is the concept of virtual grounding. If we connect 1 volt here, this also shown as 1 volt. Whatever the voltage at this point, the same is reflected at this point. If I am grounding here, this is physical ground and this is a virtual ground. The same voltage appeared here. Okay. Applications: inverting amplifier, non-inverting amplifier, voltage follower, difference amplifier, and many more. Inverting amplifier. Inverting amplifier means I am giving input signal to inverting input terminal, and positive pin is grounded, negative pin is connected, inverting pin is connected to signal, and non-inverting pin is grounded, then it is called inverting amplifier. In the name itself, it inverts means it changes the phase to 180 degree. So it is like this. If I shift this one to 180 degree, means if I shift this to this side, what I'll get, like this. Okay, so I will get a 180 degree shifted version of this one. Means I am just shifting this one like this. I am shifting this one like this. Actually, here also I have signal, and here also I have signal, right? If I shift this one to this side, means this portion I will get it here, and this portion I will get it here, something like this. So output is amplified inverted version of input signal. So Rn and Rf are input and feedback resistors. Okay. So this is grounded. Always, preferably, we will go for negative feedback. Negative feedback means the output should be connected to negative pin of the input, not positive pin. Okay. If we connect to positive pin, it will oscillate, act as an oscillator, which is unstable. For a stable operation, always we prefer a negative feedback, connecting feedback output voltage to negative of input voltage, always, whether it is inverting or non-inverting amplifier. Okay. Inverting amplifier is one in which the output is exactly 180 degree phase shift with the input signal. Apply positive voltage will give the negative output voltage. I am giving a plus 10 volt, let us suppose. Here I will get a minus 1000 volt like this. So what we assume, Vd is 0, the node A is grounded, potential, and the current I1 through R1 is I1 equal to V1 by R1. Now what is this? So this is I1, right? What is this? Current equal to potential difference by resistance. This is 0 means this is also 0. Potential difference V1 minus 0 by R1, that is I1. Okay. The same, this current, this won't allow any current into this. So this ought to go through this region and enter into this. Okay. So this current and this current are same. It won't allow any current into this. Then what is this current? 0 minus V0 by Rf. So we can equate these two. V in minus 0 by R1 equal to 0 minus V0 by Rf. The same current flows in both the resistors. So that we can obtain an expression like this.